Hello students and welcome to the 50th lecture on particle physics. And in the last lecture we were discussing about delta S delta Q conservation rule, and I told you that if delta S is equal to 0, that means the change in strangeness quantum number is 0, then the process will be Cabibbo favored when we will take into account the change in the charges of hadrons, charges of change in the strangeness quantum number. This is plus 1 or minus 1. We have Cabibbo suppressed processes. Then if delta S is equal to minus delta Q is plus minus 1, this is a forbidden process. Now, yesterday we took many examples from the semi-leptonic decays where we had A decaying into B plus a lepton and a neutrino or anti-neutrino associated with that. Today, first we are talking about the hadronic decay modes. That means we have the particles as the hadrons in the final state, and therefore we have the leptonic decay modes, semi-leptonic decay modes, and the hadronic decay modes or non-leptonic decay modes. And here I have taken the example of a lambda decay, which is decaying into proton plus pi minus. As we know that lambda is a neutral particle, its strangeness is minus 1, its charge is 0, and proton strangeness is 0, pion strangeness is 0, while proton charge is plus 1 and pi minus charge is minus 1. Now, the change in strangeness quantum number is plus 1 and delta Q is equal to 0. Therefore, if you look at the quark structure of this is UDS, this is UDU, and this is U bar D. Therefore, the catch is a S quark is changing into a U quark. Now, at the quark level, how we can understand this? We have lambda particle which is made up of U, D and S quark, and then this particle is emitting a W minus, and as it will emit W minus, it will get converted into a U quark because this charge is 2 by 3rd and this charge is minus 1 by 3rd, and this remains a D quark, this remains a U quark, and then this W minus is giving rise to a U bar D quark. Charge is minus 1 by 3, here charge is minus 2 by 3. Therefore, the total charge in the outgoing state is minus 1 and W minus is carrying the negative charge. This is what we write at the quark level, and as you can see that the transition is taking place from S to U. That means this is the transition between the two different generation. Therefore, this should carry a vertex factor of sine theta c, and that means this will be a Cabibbo suppressed process, and this has been observed to have the branching ratio of 64%. Now, if you talk about lambda decaying into n pi 0, this branching ratio has been found out to be 35.9%, and as you can see that S is minus 1, that means for lambda, n and pi they are strangeness 0 particle, and Q is 0, change in strangeness quantum number is 0. Now again here we see that we have a lambda UDS, this n is UDD, and this is U bar U or D bar D. Now what is happening? There is no change here because we need UD, and then this is emitting a W minus, and this W minus is giving rise to a D quark and a U bar quark, and as S is emitting a W minus, it is getting converted into a U quark. Therefore, this is U bar, that stands for pi 0, and this is UDD, that stands for a neutron. Therefore, a lambda is getting converted into a neutron and a pi 0. Again, you can see that S is changing into U, and therefore this will be a Cabibbo suppressed process. Now, we take another example where a sigma minus is changing to n plus pi minus. The branching ratio for this is 99.85%. That means if you take 10,000 sigma minus, then 99,985 times you will observe a sigma minus to decay into n plus pi minus. Since sigma minus is made up of dd and s quark, while neutron is ddu and this is u bar d, therefore what you see that you have dsd. This s is emitting a w minus, and that is giving rise to a u bar d quark, and then we have a dud here. Dud means we are talking about neutron, and this is u bar d, that means we are talking about a pi minus. And as you can see that this is a conversion of s to u, conversion between the two different generations, and that will carry sine theta. Similarly, if we talk about sigma plus, then sigma plus is UUS quark and proton is UUD. Pi 0 is again U bar U. You can have a diagram where a S quark is emitting a W minus and getting converted into U, and then you have a U bar here and UUD here. Similarly, you can think of sigma plus, whose branching ratio here is 48.3%, and that means if you add them up, this will turn out to be 99.9%. Therefore, 99.9% of the time, a sigma plus either decays to p plus pi 0 or n plus pi plus, and moreover, the first one dominates, and this you can see that why it dominates, because the mass of proton is 938.2, mass of pi 0 is 135, while here mass of this is 939.5 for the neutron. Pi plus is almost 140 MeV, that is exactly 139.6 MeV. Therefore, you see, you have to create massive particle, not much difference, 1.3 from neutron to proton, and then about 5 MeV from pi 0 to pi minus. Therefore, the difference is of about 6.3 or 6.5 MeV, and that means you have less phase space in this case, and therefore the chances in this case, because of that difference of 6.3, this becomes 48.3%, and this dominates, where you are creating particles of less mass. Okay, then we come to the other case, cascade 0. These are all hadronic decay modes. These are either baryons and mesons. Baryons and mesons that we are talking about. A cascade 0 decaying into lambda plus pi 0. Straightness quantum number for cascade 0 is -2. For lambda it is -1. For pi 0 is 0. You can see that delta S is equal to +1, and it is happening 99.52% of the time. And as you can again see, you can think of other particles, but you will find that the others are not possible. For example, we have discussed in the class that in principle a sigma 0 can decay into n plus pi 0, but this involves the change of the straightness quantum number by 2 or more than 2 units, and therefore this will be a forbidden process. And at the quark level, we see it by looking at this concept that cascade 0 is made up of USS quark, while this is UDD and this is U bar U. Therefore, you have to convert 2 strange quarks to 2 non-strange quarks, and that means you need 2 W exchange diagrams, and that will be forbidden process. Then in principle, that forbidden does not mean that exact conservation law is not allowing it. But if you talk about trillions of events, then also you are unable to observe even a single event of such decays, and that is why we are saying that these are forbidden decays. Then cascade 0, lambda 0 plus pi 0. as you can see that this happens 99.52% of the time. But wherever you have delta S is equal to +1 or -1, that will be a Cabibbo suppressed process, as this will involve transfer of strange to non-strange quark, S to U quark at both the places that you can see that S is emitting a W minus, and that is giving rise to du bar quark. Now similarly, we consider other hadronic decay modes, omega minus decaying into lambda plus K minus, and omega minus decaying into cascade 0 and pi minus. This branching ratio is 67.8%, and this branching ratio is 23.6%. As we have drawn the different quark diagrams in your spare time, you can draw the quark diagrams for all these processes which I have mentioned here, for which the branching ratios have been presented. You can see that this is -3, -1, -1, therefore delta S is +1, final minus initial, and then charge. As you know, these are all hadrons and charge has to be conserved, but to just for the completeness sake, you can see that delta Q is equal to 0 and delta S is equal to +1. Here -3, -2, and this is 0, and this is Q is -1, 0, -1. Therefore notice delta S is equal to +1. Here notice -3, -2, 0, charge is -1, -1, 0, delta S is +1. And similarly here strangeness is +1 for K plus, these are zeros. For charge, this is +1, this is +1, this is 0, delta Q is 0, delta S is -1, and similarly you can work out for the other ones. And again you see that K plus is decaying into pi plus pi 0, and K plus is also decaying into pi plus 2 pi zeros, and that means you have to additionally create a particle with a mass of 135 MeV. And that means this is 139.6 plus 135 plus 135. That means in total 270 plus 140. That will be the total mass that you require. And this is 410 MeV. And that is why if this is allowed, this will have more phase space to create these particles, while here you will have less phase space. That is why this branching ratio is 1.8%, while the branching ratio for this is 20.7%. And this we have to keep in mind, that when we are talking about K plus decaying into pi plus pi 0, this strangeness is +1, 0, 0, charge is +1, +1. As you can notice, delta S is -1, delta Q is 0. This will be Cabibbo suppressed process. Cabibbo favored will be the one where we have delta S is equal to 0. Therefore, we have leptonic decays like pi minus decaying into mu minus nu mu bar, where only the leptons are involved. We have semi-leptonic decays like lambda decay, where you have a baryon or a meson, and then you have leptons, these are semi-leptonics, and then you have hadronic decays like we have discussed here, where only the baryons and mesons are involved. That means particles where strong interactions are responsible for the, if we are talking about K plus pi 0, therefore all these particles which are participating in the strong interaction, they are being considered. While if you look at the isotopic spin, this isotopic spin is half, this is 1, this is 1, while I3 is plus half, plus 1, 0. Therefore, you can see that you are not conserving I, you are not conserving I3. Therefore, this will be a weak decay. Therefore, whatever we have considered, these are weak decay, examples of weak decay processes, and we know that the strange particles cascade, sigma, lambda, omega, kaon, they decay via weak interactions. Though they are produced via strong interactions in pairs, one with a straightness -1 and another with a straightness +1, they are produced in electromagnetic interaction through strangeness quantum number +1 and strangeness quantum number -1 particles, because strangeness is conserved in electromagnetic as well as in strong interaction processes, while in the case of weak interaction you can have the production of single kaon or single lambda, or you can have a single sigma, etc., and there strangeness is not conserved. Therefore we have the production of strange particles through strong interaction, through electromagnetic interaction, as well as through weak interaction processes, but these particles decay via weak interaction. Now these are the other examples which here we have listed. As you can see, a K0 is decaying into pi minus plus E plus nu E. That means this will be a semi-leptonic decay. And as I am talking about K0 decaying into pi minus plus E plus nu E, you can see that straightness quantum number for K0 is +1. For this is 0, charge is 0 and -1. Therefore, delta S is -1, delta Q is -1. This will be Cabibot suppressed process, but at the same time I have written allowed because I have also given the examples where we have the process or the decay is forbidden. For example, with the second one, K0 decaying into pi plus E minus nu E bar. Mind it, we are conserving charge, we are conserving lepton number, and we are conserving energy and all that, but straightness quantum number here is +1, 0, the charge is 0 and +1, and as you can see, delta S is -1, delta Q is +1, and that means we are not obeying delta S delta Q rule, and that means this is a forbidden process. At the quark level, you can understand this. This pi plus is a U bar D quark, and K0 is straightness +1. That means this should be S bar, and we have to have charge 0. Therefore, this will be DS bar. Okay, this is DS bar, where straightness is +1 and charge is, total charge is -1/3 and +1/3. Therefore, total charge is 0. And here this is pi plus, this is pi plus. Pi plus means this should be U and D bar. Therefore, you can see that S bar is converting into D bar. And what is this? You have the charge of S bar is +1/3. Charge of D bar is +1/3. Therefore, there is no change there is in charge, while S bar is converting into D bar, and we have seen that flavor changing neutral currents are not allowed. Therefore, you can have conversion of D to U, but you cannot have conversion of S bar to D bar, and therefore this process is a forbidden process. Similarly, you take the example of K0 bar decaying into pi plus E minus and nu E bar. Therefore, when you have K0 bar decaying into pi plus E minus plus nu E bar, this strangeness K0 bar is -1, this is 0, charge is 0, this is +1, and that means you are obeying delta S delta Q rule. This will be a suppressed process because delta S delta Q is +1, Cabibot suppressed. At the quark level, when we are talking about K0 bar has a straightness -1, its charge is 0, therefore this will be D bar S, and this is pi plus, this is U D bar. Therefore, D bar is there. What is happening? S is getting converted into U, transformation between the two different generations, and therefore this will be allowed, but Cabibbo suppressed process. And similarly, you can talk about the other guys which I have listed here. You assign them a strangeness quantum number and charge, and then see that what is delta S and delta Q. If, for example, if I consider the last one, K0 bar plus P decaying into sigma plus pi 0, this strangeness is minus 1, 0. This is minus 1, 0. Charge is 0 plus 1 plus 1, 0. That means delta Q is 0. But delta S minus 1 here, this is minus 1, and then minus of minus 1. That means this will be K0 bar. This is minus 1, and sigma plus is minus 1. Therefore, the total charge that is getting changed is not by, here it is changing by 2 units. Here it is all right. This charge is minus 1. This charge is, strangeness is plus 1 in the case of K0 bar plus P going to K plus N. Strangeness is plus 1. This is minus 1. Net strangeness change is plus 2. But this is wrongly written. This should be not delta is equal to plus 2, but this will be delta S is equal to 0. And when delta S is equal to 0, delta Q is equal to 0, then that means we have to see that what is happening over here. This is a special case. Just let me spend a few minutes on discussing this example. We are writing K0 bar plus P sigma plus pi 0. Therefore, charge is getting conserved, plus 1 here and plus 1 here. And then strangeness we are talking about, this is minus 1, this is minus 1. Delta Q is 0. Therefore, the net change in strangeness is 0. And this K0 bar is made up of d bar S quark. This is d u d quark. This is sigma plus. Sigma plus is made up of, strangeness is minus 1, charge is plus 1, u S quark, and this is pi 0. This is u bar u. Therefore, notice you have d bar S, S you have all right. Then you have d u d, d bar to u bar. Everything is fine. And then you have S, and there is no transfer then into different generation. Therefore, this will be a favored process. This will be a favored process. Therefore, this example which we have written, wrongly we have mentioned that this is forbidden and delta is equal to 2, though it should be delta is equal to 0, and it is a favored process. Therefore, you have to check that the results which we have written, whether those are correct or not, allowed, forbidden, you may take it as a quiz and see that whether delta Q is 0, delta S is the numbers which we have written, they qualify to the numbers which, to the particles which we have mentioned on the left hand side. This is how you can understand the leptonic, semi-leptonic and the hadronic decay modes, and how some of them are forbidden and how we consider that some are allowed and some are Cabibbo suppressed. Now, let us come to the charm quark, where I had promised that there exists also a rule when you have a charm quark, either that is a charm meson or you have the charm baryon. The charm quark number is represented by C, and I had told you in the last class that C is plus 1. The rule is applied to hadrons only, as the strangeness and charm quantum numbers are applied to the hadrons. And allowed plus Cabibbo favored is the one where delta Q is delta S is equal to delta C, that is equal to plus 1. That means change in the charge, change in the strangeness quantum number and the change in the charmness quantum number is plus 1, and if it is minus 1 overall, that means final minus initial, or yet you take initial minus final, that should be, if that is obeyed, then it is a Cabibbo favored. The Cabibbo suppressed one is the when the net change in straightness is 0 and net change in the charge and charmness of the hadrons is either plus 1 or the minus 1. They are Cabibbo suppressed. And the forbidden ones are the delta S delta C is equal to minus delta Q, or delta S delta Q is minus delta C, or delta S is equal to 0 and delta C is minus delta Q. Therefore, here instead of delta S is equal to delta Q is equal to plus 1 and delta S is equal to delta Q is equal to minus 1, which we called it as Cabibbo suppressed, and then we talked about delta S is equal to 0 as the Cabibbo favored process. Here we are talking about a different criteria when charm quarks are also present. Delta AQ, delta S, delta C is plus 1 or minus 1, then these are favored. If delta S is 0 and delta Q, delta C is plus 1 or minus 1, those are suppressed. And if delta S is equal to delta C is equal to minus delta Q, or delta S is equal to delta Q is equal to minus delta C, or delta S is equal to 0 and delta C is equal to minus delta Q, these are forbidden processes. Now here we have taken some of the examples. For example, D plus decaying into pi plus K0 bar. Charmness quantum number is plus 1. Pi plus no charm quark. K0 bar no charm quark. Therefore, delta C is minus 1. Strangeness D is non-strange meson. Pi plus non-strange meson. K0 bar strange meson with strangeness quantum number minus 1. And then charge has to be conserved. Therefore, this is delta C is equal to delta S is equal to minus 1. And what you are seeing that you have a D plus which is made up of CD bar. Therefore, C is emitting a delta W plus, and that W plus is getting converted into U and D bar to give rise to pi plus. Therefore, there is a conversion of C to S, and C to S belongs to the same generation, and therefore this will be a Cabibbo favored process. Similarly, if we talk about D0 bar getting converted into pi minus and K plus, now D0 bar has the charmness quantum number minus 1, pi minus has charmness 0, K plus has charmness 0, while the strangeness quantum number for K plus is plus 1, for the other two those are 0, and then we have to conserve the total charge, delta Q is 0. Therefore, what is happening? A charm quark, you have an anti-charm quark here in this case, du bar. This anti-charm, which has a charge of minus 2 by 3, is emitting a W minus, and that W minus is giving rise to a du bar quark, and as it has emitted a W minus, therefore to conserve total charge, it has to get converted into S bar, because S bar charge is plus 1 by 3. Therefore, minus 2 by 3 is getting converted into plus 1 by 3, and this is the transition between the same generation. Therefore, this will be a Cabibbo favored process. Therefore, here we have given the examples of when charm quark is present, well, how many of them are Cabibbo suppressed or Cabibbo favored or Cabibbo. In general, we say that Cabibbo allowed, but it will be either favored or suppressed, and that means either it has, if it is favored, then you have to use at the vertex cosine theta c, and if it is suppressed, then you have to use at the vertex sine theta c. If the forbidden, that means that is not allowed. Therefore, like in the previous example for the strange quarks, here you can just verify the numbers which I have written, that whether they are correct or not. Remember one thing, D plus and D0, they have the charmness quantum number plus 1, while D minus and D0 bar, they have charmness quantum number minus 1. And with this in mind, you can verify all these examples which I have listed, take them as a homework and complete this so that a good understanding of delta S, delta Q rule in the stainless sector and delta S, delta Q and delta C rule in the charm sector, you will be able to grasp the basic concept. Let us stop here and we will start from core confinement in the next lecture. Thank you very much.